Hello and welcome to Math 275 Differential Equations at Cañada College. My name is Lapuz, and in this problem we are trying to solve for a Cauchy-Euler. This is a Cauchy-Euler second order. Non-homogeneous. Initial value problem. Okay, so in solving for this problem, we are interested in first solving for the associated homogeneous equation, and actually IVP, and then use Green's function to solve for the non-homogeneous portion. All right, so that's going to be our plan. So first, solve the associated homogeneous IVP, and that is going to be pretty much the same, except it's going to be set equal to 0. Okay, and to do this, we're going to need to solve the auxiliary equation. And just to be clear, this is slightly different from our first auxiliary equation. So we're going to solve for the Cauchy-Euler auxiliary equation, and that is going to be obtained by looking at the coefficients of these three terms, and the a is equal to 1, so we'll start off with an m squared, and then the b is -1, and the middle term will have a b minus a, so it's going to be a -1 minus a, which is 1, and that's going to be times m, and then the c term is just 1. So this is m squared minus 2m plus 1, and we're going to set that equal to 0, but I think that factors to m minus 1 quantity squared. And so we have a root of 1 with multiplicity 2. So your fundamental solution are going to be y sub 1 will equal to x to the first power, and then y sub 2 will equal to x to the first power, and since it's repeating, we're going to tack on an ln x next to it. So here are your two fundamental solutions. And then your general solution, therefore, will look like y sub h is equal to some constant c1 times the first function plus some other constant c2 times the second function, which is x times ln x. From here, we'll use the initial conditions, so we will need the derivative. So let's see if we can insert a couple of equations here. We'll have the original function here, and then we'll have y sub h prime. It's going to be the derivative of that, so that's just c sub 1. The derivative of x is 1. And then we need to use the product rule. So it's the derivative of the first. That's c sub 2 times ln x plus the first. That's c sub 2 times x times the derivative of ln x, which is 1 over x. Now what we need to do is we need to take these equations and put in our initial conditions. So our initial conditions have an x value of 1. So let's take this away, and then we will insert 1 in for x, and then 1 in for x, but ln of 1 is going to be 0, so this will disappear. So that means the first equation will just be c sub 1 and plus 0, and then this is supposed to equal to our first initial condition, which is 4. So we're going to get c sub 1 is equal to 4. And then for our second equation, we get c sub 1, it's just a constant. We're going to put in 1 in for x. And this whole thing actually cancels. So we can just get rid of that. And then we will get the second equation to be c sub 1 plus c sub 2. So the second term goes away, but we still have a c sub 2. And this is equal to, according to the initial condition, it's equal to 3. So then we'll have 3 here. All right, what are we eventually going to get? It looks like we'll eventually get, oops, too much. Let's simplify this. Well, c sub 1 is going to be equal to 4. And then c sub 2, if c sub 1 is equal to 4, c sub 2 will be equal to negative 1. So let's put negative 1, c sub 2 equal to negative 1. And these would be our solutions, or our constants, and now we get the solution to the first initial value problem. So then now we can write our IVP solution. H of 0 is going to be, this is going to be 4, and then minus 1. Okay, so that's the first part. We got this done. Now, next we're going to solve the IVP, this IVP, but this time we're going to assume that these are set equal to 0. Okay, and we are actually using Green's function. So how are we going to do that? We need to build from this. By the way, this equation that we're looking at, the non-homogeneous equation, remember that it is very important that the coefficient of this y double prime is actually equal to 1. So we actually need to find, officially find the function f of x by dividing that out. So if we take our differential equation and let's divide out by x squared, I will have for my middle term 1 over x, and then I will have a 1 over x squared. And then if I divide this by x squared, this is just going to be 1. So it's important to note here that our function f of x is actually equal to 1. Okay, so now that we know that, we can proceed with finding Green's function. We found our f of x. We need to next find the Wronskian. And the Wronskian, let's see, we usually want it to write it as a function of t. So we'll write the y1 and y2 functions of t. And so we're going to want the determinant of a 2 by 2 matrix where the first function is x, well actually t, and then the second function is t times ln t. And so the derivative of the first function is 1, the derivative of the second function is the derivative of the first times the second plus the first times the derivative of the second. Well, the derivative of ln t is 1 over t, and so we have t divided by t, which is just going to be 1. All right, and so that is going to be t times ln t plus t. Oops. I think I distributed it already, so let's distribute it already. Ln t plus t, that's the diagonals being multiplied together, and then we're going to subtract 1 times t ln t. And you can see that there's an t ln t, and then there's another t ln t that's going to cancel, so I think this just simplifies. The Wronskian just becomes t. All right, now Green's function is going to be g of a function of x and t, and this is equal to, it's going to be a fraction, and we know that the Wronskian in the denominator is just going to be equal to t, so let's go ahead and just insert the t there. The numerator is going to be the first function in terms of t, so that's just t, and the second function in terms of x, so that's x ln x, and then we have a minus, and then it's the first function in terms of x, and then the second function in terms of t ln t. All right, now I think we'll see that there's a couple of t's that would cancel, one for each term, and then the t in the denominator would be gone, so that would leave us with just the ln x for the first term minus, and then this t in the second term will go away, so this is going to be x ln t. So that's Green's function. And then we'll also recall that f of t is equal to 1. So we found that in the first step here already, that f of x is equal to 1 in this case, and so f of t will also equal to 1. So in fact, we can just put f of t is equal to 1, and we'll use this into the integral. So then our particular solution will be a y sub p. Let's just write it here. Y sub p, and this is equal to the integral with the lower limit of 1, because that's your inside, or that's your boundary. That's your initial point, and then your upper limit is going to be the variable x. And then we'll put Green's theorem in there. So we found Green's theorem already. And then we're going to multiply it by f of t, which in this case is just 1. All right, so this is what we're working with. And let's see. If we integrate this with respect to t, that's just going to be t. It might be worth splitting up the integral, so let's split up the integral. So let me do this kind of in a clunky way by copying and pasting. So the first integral is just going to be this. And then the 1 doesn't make sense anymore. And the second integral is going to be a minus, so let's put that negative out here and get rid of this negative, and then it's just going to be this term here, x ln t. All right, well, this is an integral with respect to t, so this x ln x for the first integral is just constant, so let's move that out. This x here is a constant, so let's move that out. And then we're just integrating. The first one is just t, and then the second one is going to be whatever the integral of ln t is. So the first integral here is just going to be t. And then we're going to need to evaluate that integral from 1 to x. And then our second integral, this is a little bit tougher, but if you do a, well, you can try to remember the formula, or you can try to do integration by parts. But I think eventually this is going to be t times ln of t minus t. And then again, you're going to integrate this from 1 to x, or evaluate it from 1 to x. All right, so let's continue on with this. And this part here is just going to be x minus 1, because that's just t, and we're evaluating it. And then now this part here will be, this whole thing will be replaced with x's. So let's replace it with x's. X, that's the top limit. And then minus, and then it's going to be the same thing, except we're going to replace it with 1. So this is going to be 1, and then we'll have ln of 1. ln of 1 is 0, so that goes away, but this is not going to go away, that last one. All right. Let's keep working with this. So let's say equals here. Let's distribute this, so this x gets distributed. I'm sorry, this is x minus 1. What happened? This is supposed to be 1, x minus 1. All right, now let's distribute. Distribute this x. Oops, this is 1 again. Sorry. Let's distribute the x, so this will become x squared. X squared, and then minus 1, so that's just minus x ln x. So that's the first part here distributed out. Now we have an x that needs to get distributed here. So this first one is going to be an x ln x, or x squared ln x minus x squared. So let's deal with that first. So let's write x squared ln x minus x squared. So that gets rid of this part. Oh, but there's a negative in front, so this negative plus a negative will become a positive. And then now this is 0. And then we just have a negative in front with, that's the negative in front here, and then another negative, and then another negative. So that's 3 negatives. That's going to end up being negative, and then it's just going to be x. So this whole thing will just be a minus x. And everything else is gone. All right, so hope that simplification worked out. One more thing to probably simplify here is that this x ln x, or x squared ln x, and this x squared ln x are both the same. One's a plus and one's a minus, so I can just get rid of one of them. I actually get rid of both of them. So this is gone, and this is gone. Okay. So I think we have our solution here. And this is our particular solution. So let's just get that written down. We have y sub p is equal to this expression here. Okay, now that we have that, we have the y sub h. So finally, the solution to the IVP is given by, so this is going to be a y equals 2, and then we can just take this solution for y sub h that we got, and then we can add on the solution that we got from here. Okay, it looks like these two are the same, so I think we can combine them. They're both negative, so that's going to end up being a negative 2. So let's just rewrite everything over again. And just call this a negative 2. And this is it. All right, I hope that helps. And just a quick summary, a rundown. We solved for the associated homogeneous equation that actually uses the initial value conditions. To use Green's theorem, we solve for the non-homogeneous differential equation, but our initial conditions change to just have that equal to 0. And then we use Green's function, and remember, in order to use Green's function, we're going to use the f of t, and the f of t has to come from the non-homogeneous equation where the coefficient of the y double prime is equal to 1. And so in this particular scenario, it turned out that the f of t is just equal to 1. So we find the Wronskian, which is part of Green's function. Green's function has this expression where the Wronskian's in the denominator, and you're using the y1 and y2 solutions that we got from the homogeneous portion. And then we integrate from the initial condition, initial starting point x, to the random variable x, and then we're integrating with respect to t. Anything that does not have a t is deemed a constant. So we can take that out and just integrate with respect to t, and then we should, after everything's all said and done, there's going to be no more t variables and just going to be the x variable and possibly constants. And then we tie in those y sub h and y sub p together to get our solution, simplify if needed, and that's it. Okay, good luck. I hope that helps.